I'd like to introduce Eric Chaisson, who is the director of the Wright Center for Science Education at Tufts University, and also professor of physics and of education there. In addition, he's an associate of the Harvard College Observatory, where he teaches astrophysics, and he's co-director of the MIT Space Grant Consortium. I'm surprised he had even the time to come to this meeting with all of those commitments, plus 11 books which he has authored, one of which, Cosmic Dawn, has won several awards. His most recent book, The Hubble Wars, also won the American Institute of Physics Award for Distinguished Science Writing. And he is co-author of Astronomy Today, the most widely used college text in the United States on that subject. So it's with great pleasure that I introduce to you Eric Chaisson.
Okay, thank you, Peter. Good morning, everyone. Thank you for inviting me to spend some time with you this morning. I am an astrophysicist, as Peter mentioned, and that means essentially that I've been trained in physics and I've adopted the universe as my laboratory, but given the previous remarks by Professor Rappaport, I can assure you I've taken all of the equations out of this talk, but not all of the results of the equations, perhaps. I do want to assure you this morning at the outset that this is a very exciting time to be an astrophysicist. I would imagine that when the historians of the future look back at this part of the 20th century, they're likely to conclude that we are now living, still in the 20th century, in a golden age of astrophysics. I say this simply and quickly because in a single generation, not the generation of my children and not the generation of my parents, but our generation, we are opening up the entire electromagnetic spectrum, viewing the universe, or perceiving perhaps the universe in all of its available wavelengths, and we are seeing, as Galileo said hundreds of years ago, wondrous things. But by the same token, I think the historians of the future, hundreds of years into the future, when they write the books and look back at our times, they're also likely to conclude that we are now living in a golden age of biochemistry. Because the advances in the biomedical sciences are equally as impressive, in my opinion, as those being made in the astrophysical domain. In fact, I wish I had been a biochemist. Now, I mentioned these two subjects, these two interdisciplinary subjects, astrophysics and biochemistry, for a couple of reasons. One, I think these two subjects, more than any others, are changing the way we view the universe and view our role in the universe, if we have a role. And secondly, I mentioned these two interdisciplinary subjects because in my work, in my research, in my teaching, in my writing, I'm trying to work in each one of these areas. And furthermore, and perhaps more fundamentally, I'm trying to bring these two areas together, these two interdisciplinary subjects of astrophysics and biochemistry, into a grander interdiscipline, a transdiscipline, if you will, and that is what I call cosmic evolution. Now, I'm not certain if anyone has defined cosmic evolution, so I'll make a stab at it right now by simply saying that cosmic evolution is simply the study of change through time. More particularly, I would define cosmic evolution as the study of the many varied changes, developmental changes, generative changes, in all things, all radiation, all matter, and all life, throughout the entire history of the universe. Change is essence here. Change is the hallmark. Change is the key to the origin, the maintenance, and indeed the destiny of all things. Two caveats before we proceed. First, when I say cosmic evolution this morning, I'm not just talking about astronomical systems. I'm talking about all such systems, the near and the far, the big and the small, the past and the future. Consequently, the kind of evolution we're most familiar with, biological evolution, neo-Darwinism, becomes just one subset of a much grander evolutionary scheme stretching across all of space and all of time. The word evolution should not be the exclusive purview of the biologist, nor should the word selection. Second caveat, when I say this morning cosmic evolution, I'm not trying to take the essence of neo-Darwinism, the principle of natural selection, and extrapolate it on into the universe. I'm trying to do more than that. I'm trying to ask whether there might be a common denominator, a factor, a principle, a law, something that will enable us to reach beyond the principle of natural selection is applied to biological systems, and ask whether there might be a principle of cosmic selection applying to all systems universally, based on the universal change I see. Whether I look at the universe with a Hubble telescope or look down the other way with a giant accelerator at CERN, I see change on all scales. In effect, we're trying to build a cosmic heritage. It's a heritage because it's a structure of understanding that comes to us out of the past. As an astrophysicist, I look out into space, I'm looking back into time. It's a heritage because it's the structure which I claim, if we're smart now at the present, we will grasp. And it's also a heritage because I claim that if we're wise as well as intelligent, or perhaps if our children in the future are wise enough to embrace it, they will in fact have a roadmap to the future if they are to have a future. In effect, although it sounds very arrogant and pretentious, but when time is short and I have about 30 minutes to talk about 12 billion years, no problem. 29 minutes, sorry, I'll never make it. It does sound pretentious when I say that what we're trying to build here is a cosmology in which life now has a role. In effect, a scientific philosophy, a new philosophy in which there's great emphasis placed on that adjective, scientific. Because I think we're trying to bring the power, and it is a power, of science and technology to bear upon some of the most fundamental questions that the philosophers and even the theologians have asked time immemorial. You know the questions as well as I do. Very quickly, who really are we? Where did we come from? Where did everything around us come from? The air, the land, the sea, the earth itself, the points of light in the nighttime sky. What is the origin of all these things, all these systems? Why is there so much order and structure and complexity out there? Why does it seem in our gut and in our mathematics that complexity increases with time? Can we square, can we reconcile the evident constructiveness of cosmic evolution among the galaxies, stars, planets, and life forms with the evident or theoretical destructiveness of the second law of thermodynamics? In effect, with this new kind of thinking, but based on old science, there's no new science here. Perhaps we can begin to address the most fundamental query, to wit, now, why is there something rather than nothing? Now, the first set of slides, which I'm assuming if I just ask for them will appear, although maybe I will have to do something. There's a box here. I have a box like this in my classroom at Harvard. We call it the idiot box for those who can't work it. And I'm still trying to program up. I'm looking for the, let's see, projector, screen, projector, down, up.
Help is on the way.
Help is on the way to determine how I get to the next page. Volume and lighting, slides. Good. Okay. Then,
Keep the right.
ah, yes. Try that. Thank you very much. Okay. I'm going to work with pairs of slides. Generally, on the slide closest to me, there'll be a somewhat more technical slide than the slide farthest away. Indeed, if you're having trouble with this first set of slides, the slide on your right is the less technical slide here in this pair. I utilize the arrow of time as my archetypical symbol. There's a lot of information based and embedded within this one particular image. I would spend back at Harvard in my course a good 53 minutes, an entire module. I work in 53-minute intervals. An entire class just talking about all of the implications and all of the assumptions that go into this arrow of time that stretches on this slide from left to right, from the beginning to now, from Big Bang to humankind. But I see just briefly here in this talk several important key features stretched across the top diagonally. I see it in particular that there's a thread of change linking many of the major systems that have emerged over the course of time, or perhaps many of the major evolutionary epochs that we can identify and date over the course of time. We can see at the top how some of the atoms came together to form galaxies by methods we don't quite understand in detail. We can see how the galaxies gave rise to environments that enabled stars to emerge. We can see how the stars gave rise to the building blocks of life. The building blocks of life in chemical evolution gave rise to life. And life has now evolved into the kind of culture and technology that we now share. Consequently, again, I repeat that biological evolution, in this scheme of things, in the penultimate diagonal at the top, becomes just one subset, albeit an important one, stretching across an evolutionary scheme that covers all things throughout all of history. And what Darwinism does for plants and animals, in effect, cosmic evolution aspires to do for all things. Furthermore, in effect, if Darwinism created an intellectual revolution by freeing us from the notion that we as human beings are any different from any other life form on the surface of the earth, then it would seem to me that cosmic evolution is destined to extend that intellectual revolution by freeing us from the notion that the atoms and molecules in our body are any different from the atoms and molecules in the stars and galaxies beyond. Again, there's a great deal of information embedded in the construction of this simple arrow of time. Is it pointing anywhere? I don't think so. Is it pointing at us? No. Is it anthropocentric? I don't think so. Is it a story about us? Yes. I think it's a story about us, as well as other systems. Now, the gut feeling that we have for this meeting is that if we take a look across the arrow of time, we have the gut feeling in this qualitative plot of time from the Big Bang to the present that the thing we call order, complexity, information, organization, inhomogeneity, whatever you want to call it. This is not a meeting on semantics. I'll just suggest that I'm talking about complexity, where complexity I'm suggesting a state of variety, a state of intricacy, a state of interconnectedness, a state of complication among many of the various components within a given system. You understand what I mean when I say that we have the gut feeling that over the course of all time there has been a rise in complexity. Just looking around, galaxies, stars, planets, and life forms. As we move along the arrow of time, there is a movement from simplicity to complexity, from inorganic to organic, from chaos in the old-fashioned Greek sense to order. We don't know how the curve really rises. It might rise as the middle member of the family, quite nicely, that would approximate exponentially. It might rise more gradually, as shown at the curve at the top. It might even be more dramatic than exponential. We don't know at this point because this is a qualitative plot. But this is the plot that drives me. I want to understand. And I want to know if I can understand that I want to know if I can discover a common denominator that would affect all systems, from galaxies to life forms, enabling me to put all such ordered and complex systems on the same page, and enable me, therefore, to understand the nature of this curve. I want to understand how it is that the evident constructiveness of cosmic evolution enables these systems, like islands in a great sea of chaos, to emerge out of a sea of the universal increase in entropy. Whether that complexity that grows is represented here in, let's say, a cultural phenomenon such as a stained glass window at Chartres, which this is not, or which it is, an image looking down along the axis of the DNA molecule. In either case, an expression of cultural adaptation or biological adaptation, that represents some form of complexity. Now, when we have a system in front of us, I tell my kids, my students, if you have something in front of you that you don't quite understand, immediately, at least from the point of view of a physicist advising a student, try to get a handle on two things: the density and the temperature. I claim if you have a system that you're trying to understand, and if you know those two quantities, temperature and density, you'll be able to determine quite a bit about that system. In this case, at the middle part of this talk, I'd like to suggest in the next slide that I'm trying to plot for you here the density and temperature of all things in general, nothing in particular. This is is the way the mathematical astrophysicist looks at the run of those two quantities throughout the entire history of the universe. Temperature and density, from Big Bang to humankind, from the origin to the present. In particular, using galaxies as test particles, such as in that Hubble Deep Field image at the right, I can suggest to you that the standard view of Big Bang cosmology is such that the universe began hot and dense and has cooled and has thinned over the course of time. Very simple. It looks like a frightening plot, but it's very simple. It's just suggesting again that the universe has thinned and cooled with expansion. Not expansion into space. There's nothing out there. It's the fabric of space moving out into time. So over the course of all time, in general, the universe has allowed the density to come down and the temperature to come down, and the thermodynamic conditions to change accordingly. For example, just dipping into this very briefly, although this is another, back in Cambridge, entire 53-minute discussion just based on this one plot, because there's a lot of meat embedded in here. An example is that in the early universe, where radiation was dominant, if something simple like a proton tried to come together with something simple like an electron to build the true common ancestor, a hydrogen atom, in that early universe, the radiation was so severe under conditions of very high temperature and very high density that the radiation would have broken apart even a simple atom, let alone anything more organized or complex like a galaxy, a star, or a life form. There could have been no organization appreciably in the early universe. The early universe was equilibrated. Symmetry ruled. Everything was uniform and boring. But with time, inevitably and naturally, no magic involved, as the universe cooled and thinned, those atoms became clustered into galaxies. The galaxies gave rise to stars. The stars allowed the planets to, etc., and all the degree of complexity we've been talking about in the previous curve gets scrunched up here in this logarithmic plot. There's a lot of information contained within this plot, but I can attempt to summarize for you the key aspect of what's most important about this plot by placing onto the same page those two important quantities, radiation and matter, on the same page. By plotting just simply what is known as energy densities. You'll hear me talk about energy densities for the rest of the talk. I think energy densities are at least a part of the key to understanding the origin, the maintenance, and the fate of all systems. In this case, early on, the universe was flooded with radiation. The radiation era, it says at the top. Because again, the radiation density associated with radiation, the energy density associated with radiation was much larger than that associated with matter. But because of the way the cosmology runs in Big Bang's standard cosmology these days, there's a crossing of the curve somewhere in the vicinity of the first few millennia to the first 100 millennia. Somewhere between, 10 to the 4th to 10 to the 5th years. This being, again, a logarithmic plot. I'm keeping these plots running the same way from the origin to now, over the course of 12-ish billion years. Such that eventually, naturally and inevitably of its own accord due to expansion of the universe, the curves change in such a way that, as I said in the previous slide, matter could begin to coagulate, organize, complexify, and become more wrapped up in systems. The energy density now associated with matter exceeds quite considerably by orders of magnitude, this being a logarithmic plot here as well, exceeding considerably the energy density associated with radiation. So matter can in effect rule or dominate over radiation within localized systems, those localized systems being again galaxies, stars, planets, or life forms. Now, as the universe changes here, and many people back where I come from suggest that this is the greatest change in the history of the universe, such that the universe changed from one in which there was no structure, total symmetry, complete equilibrium, into one in which there could be structures because equilibrium has broken down and structures can begin to emerge, we can plot that in such a way in a pair of, let me just see if I can get that one going, in a pair of diagrams here to suggest something fundamentally interesting. At the top we have here plotted in the conventional thermodynamic sense the degree of entropy that reigned in the early universe. I say S equals S max in the early universe prior to that great change. When radiation ruled, the universe was equilibrated. Entropy was maximized. The heat death of the universe had occurred long ago for those prevailing conditions in the early universe. But when the universe fundamentally changes, when symmetry breaks, different temperatures are required to characterize both the matter and the radiation. In the early universe, only one temperature was needed because the state was totally equilibrated. But once symmetry breaks and equilibrium is destroyed, we move into an era in the universe forevermore with expansion of non-equilibrium, in which case one needs different temperatures to describe different fields. So you set up naturally temperature gradients, other kinds of gradients, energy flows, available energies, free energies, Helmholtz and Gibbsian's energy in the kind of conventional thermodynamics that I appeal to here. It's non-equilibrium thermodynamics, to be sure. It's Pagasianian kind of thermodynamics. But it's an attempt to suggest that as the universe decouples or fundamentally changes at the top, there's a difference now, and a growing difference, between the actual entropy S and the maximum possible entropy that the universe could attain. Because the real universe, the actual universe, cannot keep up, theoretically, with the expansion. And so consequently, the difference in entropies allows us to suggest that the conditions might be suitable for the growth of information. And simply by taking, heuristically, the difference between those two entropies at the top plot, one can plot here something akin to information and show that that curve can begin to rise. Simply because in the early universe, there was no lack of equilibrium. There could have been no information appreciably. Could have been no organization, no complexity. But with the fundamental break in symmetry, the fundamental change in the early universe between the radiation era and the matter era, we now get a considerable difference or differential between those two possible entropies, and it allows information to rise. Now I'm interested in this for two reasons. One, this curve starts to resemble the curve that I was fascinated with early on in the talk, the curve of rising complexity with time. And secondly, I'm interested in these dual plots, A and B, because just by looking at them, it begins to suggest that I can reconcile a universe in which the entropy is indeed increasing in accord with the second law, with a universe in which there is also a growth of organization and complexity. But I don't know how to handle information. With all due respect to those of you who are here as strong adherents of information theory, I don't know how to quantify this well. I don't understand it really well myself. I don't understand the difference between raw information, meaningful information, etc., etc. Nor do I understand how to quantify this curve using a kind of Schrodinger-like negentropy. I've never seen an entropy meter in my lab. I, as a physicist, throttle back to the old standby energy. Just as I throttle back in considering elements of the early universe radiation and the subsequent matter that emerged from that radiation, energy densities. Because it can't be just energy alone. I know darn well that a galaxy has a great deal more energy than an amoeba. But you can't tell me that a galaxy is more complex than an amoeba. It's quite definitely the other way around. It's got to have something to do with energy per unit volume, energy per unit mass. That is, energy density. Furthermore, if I am to quantify this in ways that I can understand it, it's more than just energy density. We're talking about open thermodynamic systems, coherent systems, systems that allow the energy to come in, to flow in. So it's got to be something like energy per unit mass per unit time. It's got to be an energy rate density. Heck, it's what the astronomer calls light to mass ratio. It's what the biologist calls specific metabolic rate. It's what the physicist calls power density. Everybody's got their own term for energy per unit mass per unit time. Something like ergs per second per gram. But everybody calls it different things in different subjects. If I take the systems that I know, just in the main, broadly, and look at them quantitatively, on the page that I understand, energy, I can indeed plot now, here at the top, phi sub m, ergs per second per gram. Energy rate density, logarithmically, on the same scale I've been using throughout the talk, from the origin of the universe to the present, for systems such as galaxies, stars, planets, and a variety of life forms. I plot them in such a way that I actually calculate the flow of energy per unit time, per unit mass, through those systems, thus showing, for example, very clearly and quantitatively that an amoeba on this scale surely is a great deal more, orders of magnitude more complex than a star or galaxy. And I plot them with horizontal histograms according to the time scale over which these systems have existed on this same plot of all things. And I see an interesting curve that rises dramatically upward. Just as my gut feeling suggested in the second slide of the talk, that rise of complexity perhaps ought to be generally. And just as one of the previous slides suggested that the information content, or however you want to call it, in the later universe could well have arisen dramatically and naturally once the universe had broken its symmetry. Now, I do want to put these on the same page as well. Whoops. Here it is. By suggesting one more comparison, though be careful, I've mixed the units here a little bit. I could explain it in greater detail over lunch or some other time during the next couple of days that I'll be here. In an attempt to place all of what I've said thus far on the same page, radiation in the early universe, matter now, and life, I can plot these energy densities for radiation, for matter, and for life, and suggest that in addition to the matter era emerging from the early radiation era, there may well be, on this scale of things, another era, another great change, a life era, in which life begins to manipulate not only radiation in the form of, let us say, photosynthesis by a plant, but we begin to, more sentient beings begin to manipulate, we sentient life forms begin to manipulate matter more dramatically than matter can manipulate us. Just think about it for a moment. We are now, as technological beings, and this is not an anthropocentric statement, we are beginning to manipulate those two factors, the genes and the environment, that have led to the development of all biological evolution up to this point. We are beginning to take into our purview those two factors. We are beginning to literally take matter into our own hands. And so for that qualitative reason, there may be another whole era in which life begins to emerge as a dominant system over the matter era in much the same way that the matter era emerged naturally and of its own accord from the radiation era early on. Now, we'll hear a lot of talk about life at this meeting, and I bet you very few of you will be willing to define it. I've just come from a meeting of biologists where I spent a week talking about the origins of life. I think I was the only physicist there, and I kept challenging them, the biologists, to define their subject. Very few of you are willing to define life. I can lock 12 physicists in a room and ask what's matter, and very quickly we come to a consensus. Matter is anything that has mass and takes up space. Internationally, everybody agrees on that. But if you lock 12 biologists in a room, try to ask them what their consensus view on life is. Very difficult. I have a definition of life that I want to share with you, and it says the following. It's a somewhat contrived definition, and I'll tell you how it's contrived. It says, life is an open, coherent space-time structure maintained far from thermodynamic equilibrium by a flow of energy through it, dash, A carbon-based system operating in a water-based medium with higher forms metabolizing oxygen. I state it in that way because the first part of that definition, an open, coherent space-time structure maintained far from thermodynamic equilibrium by a flow of energy through it, can pertain to any system. A galaxy, a star, a planet, or a life form. It's only the part of the equation after the dash that then pertains specific to life as we know it. And indeed, my definition of galaxies, of stars, of planets, and other systems have this same definition up to the dash and then say something beyond. I'm specifically trying to contrive this definition, one, to provoke you, and two, to put all these systems, whether I'm talking about it in words or whether I'm talking about these systems quantitatively, on the same page, treating them in the same way, in the same manner. We can look a little bit more deeply in the last 5 minutes that I have. We can look a little more deeply. I'm not sure if that can be focused a bit. Maybe I can do that. I don't see focus anywhere. I'll just ask for some AV person behind the walls if they could focus this particular slide here. Because what I've tried to do in the remaining 3 slides is to take a closer look at the quantitative analysis of this same plot that I have generated for you. Yes, using equations over the entire history of time on the same scale that I've been using throughout, from the origin of the universe to the present. Here's the underlying plot. As we see the degree of complexity, or as I call it, the flow of free energy density through stars, galaxies, stars, planets, and life forms. I'm looking at this first of 3 plots more carefully at the bottom part of the plot, at, for example, stars and planets, and I'm noting that I can actually quantitatively see and convince you over lunch with quantitative analysis that the sun, for example, is more complex and is more organized than a protostar. Yet the sun is less complex and less organized than a red giant. Makes a lot of sense because a red giant is a more advanced, we say, more evolved star, where it has a deeper temperature gradient from surface to core, deeper chemical gradient from surface to core. You can say, aha, what about supernovae, which have a great deal of energy flowing through them? Well, I'm not talking about maximum or minimum principles here. I'm talking about optimization of flow through various systems. The drive toward complexity is not always the case. There are the bats who retreat into the cave. There are the civilizations that collapse. There are the stars that explode. Those systems simply have, it would seem, too much energy flowing through them, like any bomb or any supernova, perhaps any flame. Similarly with the planets, one can plot in greater detail, further up the plot, a variety of systems, such as the moon, very dormant, very dull, very boring, very equilibrated. The Earth and Venus, up through Jupiter, and some of the hydrothermal vents that I've plotted on there. I can plot things like planets that are wildly different in size, along with hydrothermal vents on the same plot, all the way up here, because I'm normalizing everything to the same page. I'm normalizing everything to their given mass. This is energy per unit time, per unit mass. Let's look just in the penultimate slide a little bit further up the plot, where we can look at plants and animals. I'm looking at a middle part of the plot here now, and I'm looking at it not just in words. I'm looking at it with quantitative analyses, such that I can see among different plants, I won't go into the detail, I'm mindful of the time, that one could suggest that some plants are less complex than other plants, and all the way up through animals that may be familiar to us, reptiles, mammals, birds. Birds have, of course, in addition to structure, a great deal of interesting function, such as their ability to fly. But we have, I don't know if you can see it, the ability to ride bicycles and to sew and to do other things that birds can't do. You can move up and down the plot by just following the flow of energy into various systems. Here, in this case, an analysis of various specific metabolic rates. And you can, interestingly enough, without making too much of a comment about the implications here thus far, look at the top part of the curve. still on the same quantitative analysis and take a look at different civilizations, from hunter-gatherers to the controlled use of fire up through agricultural systems, farming, and industrialization on into today. You can also look at various machines and the evolution of those machines, suggesting, in fact, that those machines are more complex than some of the systems that associated with ourselves, specifically biologically, and maybe they are. I'm not sure. I'm not suggesting, again, that this is a demonstration of anthropocentricity, nor is this slide meant to show that. I am suggesting, however, this is a story about ourselves, at least about ourselves. And it's a story about how we fit into the cosmic scheme of things. In summary, therefore, what I've tried to do today is I've tried to suggest for you a cosmic framework against which we can begin to understand the structure of all systems, from galaxies to stars to planets to all life forms and their inventions. I've suggested a way in which we can, in fact, embed life into a new cosmology, but without using demonstrably new science. I've suggested, or at least perhaps I made a reasonable case for there to be a whole new era, a life era in the history of the universe, where life emerges, not only emerges, but begins to manipulate matter and control matter and dominate matter, much as matter eventually in the early universe came to control radiation. I've suggested a way in which we can perhaps identify a common denominator, a factor, a principle, a something that would enable us quantitatively to analyze all such systems that we can see around us, whether it be on the Earth or out into space. And furthermore, I've suggested a way in which we can, in fact, reconcile the theoretical destructiveness of the second law of thermodynamics with the evident constructiveness of cosmic evolution. And for the guy in the last row who wants to ask, but how does this fit into the bigger scheme of things? The answer is, of course, this is the bigger scheme of things. Thank you very much.
Thank you, Eric. That was wonderful.
Possible to ask one question before the speakers can?
Eric, do you want to take one quick question? A quick one.
Because we're using up that extra time. We're yes.
Louder.
Can you hear me?
No.
In the early part of your discussion, you mentioned you were using the word chaos in the old sense. If you introduce the idea of chaos in the new sense into your description, would that have any implications for what is now going on?
If I introduce the idea of chaos, would that have implications for what I've said here? Throughout this discussion and throughout this analysis, I've embedded aspects of chance, stochasticity, very strongly embraced statistical physics. So I think chaos in the more modern sense would not have largely an alteration in any of what I've said here, nor would issues like dark matter and accelerating universes, and I could explain that at length later. I think this is a robust theory on very broad scales, and in particular I want to suggest that even though there are equations, even though there are many graphs, this is not an exercise in reductionism. It is an exercise in both reductionism and holism, because I strongly suggest that it's not only chaos and chance, but an element of determinism that comes together, much like Dobzhansky said long ago. Creativity arises from the mixture of chance and necessity.
Thank you very much, Eric.